Welcome to this explainer. You know, when you first set foot on an offshore process module, the visual chaos can be, well, completely overwhelming. You're instantly surrounded by what feels like this totally impenetrable maze of steel. But don't worry, by the end of our time together today, we're going to reveal the highly regulated, deeply logical order hidden right beneath the surface. We're going to demystify the incredible anatomy of an offshore platform.
The chaotic metal jungle of pipes, valves, and massive flanges might seem totally random at first glance, but it's actually a heavily structured circulatory system. Every single pipe has a critical purpose, every valve has a specific function, and every joint is mathematically calculated to withstand absolutely incredible forces. Literally nothing is left to chance here.
Okay, let's dive right into this. We'll be covering 6 key areas today: making sense of the chaos, hydrocarbon versus utility systems, decoding the color language, navigating the P&ID map, understanding valves, supports, and vessels, and finally, the codes that prevent catastrophe. Starting with part 1, making sense of the chaos and structuring the system. To begin taming this absolute maze, we have to establish the foundational rule of offshore piping. You've got to divide the entire system into 2 clear, distinct categories. Everything you see falls into one of these 2 buckets. Those 2 categories are hydrocarbon lines and utility lines. Hydrocarbon lines? Well, those are the moneymakers. They carry the crude oil, gas, and condensate. And because they carry highly flammable fluids under immense pressure, they're the primary hazard on the platform and require the absolutely strictest design standards to prevent leaks. Utility lines, on the other hand, carry everything else. Think seawater, glycol, diesel, and air. They act as the essential support network that actually makes the hydrocarbon extraction possible. Moving to Section 2, hydrocarbon versus utility lines, the platform's life support. While extracting hydrocarbons was obviously the main goal, the utility lines are what actually keep the platform and the human crew living on it alive and functioning day in and day out. They are the true lifeblood of the operation. Now, what's really interesting about these everyday utility fluids is that they're just as heavily engineered as the crude oil itself. You've got massive seawater systems designed for cooling and fighting rig fires, glycol systems for gas dehydration, diesel for generators, compressed air for instruments, potable water for the crew to drink, and carefully separated drain systems ensuring oily rainwater is safely treated. Every single one of these utility systems is a massive engineering feat on its own, running right alongside the main production lines. Section 3, decoding the color language and reading the physical space. So if you're standing on the deck, completely surrounded by all these pipes, how do you tell them apart? Engineers and technicians need an immediate visual language to identify hazards before doing any work whatsoever. And that brings us to the platform's color coding system. Think of the platform's color chart as the essential visual decoder ring for platform safety. It dictates the specific colors assigned to various offshore fluids, usually aligning with strict standards like ASME A13.1. Paint isn't just for preventing rust out here, it is a vital communication tool that speaks instantly to everyone on board. Here are the critical colors you absolutely need to know. Yellow or orange screams hazard. That's your hydrocarbon gas. Red is your emergency firewater. Green is seawater. Gray or silver indicates crude oil or condensate. Blue is potable drinking water. And brown is for drains and sewers. Assuming what's inside a pipe based purely on its size or location can be incredibly deadly. So learning this specific color code is quite literally a fundamental survival skill offshore. On to Section 4, navigating the P&ID map, the engineer's blueprint. Now we're going to transition from the physical reality on the deck to the conceptual map that engineers actually use to track this entire circulatory system. You can't just rely on painted pipes to understand the whole picture. You need a schematic. That schematic is called the P&ID, or Piping and Instrumentation Diagram. This is without a doubt the single most important engineering document on an offshore platform. It takes the physical chaos of the module and translates it into a perfectly ordered, logical blueprint showing every pipe, valve, instrument, and safety device. Being able to read a P&ID is a core, fundamental skill for anyone in the industry. So the crucial point is just how much data is packed into this map. On a P&ID, a simple alphanumeric code instantly tells you everything you need to know. For instance, a callout of 1,500 pounds CS tells you it's rated for a massive 1,500 psi and made of carbon steel. Or 900-pound DSS means 900 psi duplex stainless steel, which is built for highly corrosive, sour fluids containing H2S.
It's a brilliantly efficient shorthand.
Section 5. Valves, supports, and vessels. The muscles, skeleton, and organs. We've seen the overall circulatory system and the map. Now let's zoom in on the physical components themselves, which control flow, support the weight, and process the actual product.
Valves are essentially the muscles of the piping system, and they definitely aren't one size fits all. You have gate valves for full open or closed isolation, and ball valves that snap shut quickly with just a quarter turn. When you need to carefully throttle flow rates, you use globe valves. Then you've got critical safety devices like check valves to prevent deadly backflow, automated control valves, and safety relief valves that automatically pop open to release dangerous pressure spikes. They each serve completely different, highly specialized purposes.
The skeleton of the system is the pipe supports, and man, it's a very delicate balancing act. An undersupported pipe sags over time, creating low points where liquids pool, which significantly accelerates internal corrosion. But an over-restrained pipe is just as dangerous. When hot fluids run through cold steel, the pipe naturally expands. If it's locked down too tightly and can't absorb that thermal expansion, enormous stress builds up, and the welds will literally crack wide open.
Once the fluids are safely routed and controlled, they arrive at the pressure vessels. These massive tanks are the organs of the platform. This is where the actual money-making work happens. It's where the raw, chaotic mixture coming straight from beneath the sea is separated, treated, and stabilized for sale.
And this brilliantly illustrates the elegant physics inside the platform's most vital organ, the production separator. The turbulent well stream crashes into an inlet diverter, which breaks its momentum. Then simple gravity just takes over. The lightest element, the gas, bubbles up to the top. The oil forms a floating layer right in the middle, and the heaviest element, the water, sinks straight to the bottom. Each is then cleanly piped out through its own dedicated line.
Section 6. Codes that prevent catastrophe. The mathematics of survival. We've broken down the physical parts and the processes, but we really have to understand the foundation holding it all together. You see, none of this architecture relies on guesswork. Every single piece of steel is governed by strict, unforgiving mathematical law. Let's move to the math and see how it builds our baseline for safety. The fundamental design equation from the ASME B31.3 process piping code is known as the Barlow formula. It calculates the absolute minimum wall thickness for a pipe based on internal pressure, diameter, and the material's stress rating. This isn't just some academic equation. It literally encodes decades of failure experience into mandatory safety law. These calculations group pipes into ASME pressure classes, ranging from class 150 all the way up to an extreme class 2500. The class dictates everything to the engineer: the required wall thickness, the exact flange ratings, and even the size and tensile strength of the bolts holding the joints together. This meticulous code ensures that every single joint can withstand the immense, violent pressures of deep-sea hydrocarbons. Which brings us to our final thought. When you consider that a single undersupported pipe, or a misunderstood PNID, or a totally wrong assumption about what's inside a color-coded line can cause a massive explosion, how do these huge, heavily regulated structures continue to survive the harshest oceans on Earth day after day? Well, the answer lies in the incredible, highly structured engineering we just explored. By turning the chaotic sea into a regulated mathematical system, engineers actually tame the impossible. Thanks for joining me on this explainer, and keep your curiosity flowing.